In this video, we'll be focusing on Euclid's division lemma. Euclid's division lemma. This is the first topic that you learn while in class 10th, Euclid's division lemma, and based on its application, we have Euclid's division algorithm, which helps us to find out the HCF of two given numbers. So first of all, we'll be focusing on Euclid's division lemma, what it is, and then we'll see how to apply Euclid's division lemma in Euclid's division algorithm to find the HCF of two numbers. So before coming to Euclid's division lemma, I just wanted to ask you, what do you mean by lemma? See, lemma is nothing but a proven statement. Lemma is a proven statement which is used further to prove other statements. Lemma is a proven statement. So Euclid's division lemma, you can say, is a proven statement that I'll tell you what it is, and this statement we'll be using in Euclid's division algorithm to find the HCF of numbers. So what is Euclid's division lemma? Euclid's division lemma is a very obvious thing that you have been doing since your childhood. Only the thing is, we have never focused it in a very precise way. It says that if there are two positive integers a and b, okay, so let us say that given that two positive integers a and b, okay, there are two positive integers a and b, then there exists unique integers q and r, right? If you have two positive integers a and b, then there exists two unique integers q and r such that a equals to bq plus r, where r is greater than or equal to 0 but lesser than b. This is Euclid's division lemma. Say, like this will be more clear when I'll take an example. Say I have two numbers 24 and 7, for example. So I have two positive numbers 24 and 7. So let us divide 24 and 7 and let us see what do we get. 24 7 7 threes are 21. So the remainder is 3. So I can write 24 as 7 into 3 plus of 3, right? So we got it in this form, that is 24 and 7 can be uniquely represented as 7 into 3 plus of 3. This is what Euclid's division lemma says us. Take another example. Say I have 24 and 5. 24 and 5, I can write it as 24 equals to 5 into 4, that will give me 20, and the remainder 4, right? And always remember that this 4 will always be lesser than the divisor 5. Agree? This is what is the concept of division. So this is the division process that we have been learning till now. This is our remainder, this is the quotient, this is the divisor, this is the dividend. Only the thing is, we are writing it in a statement form, in the form of Euclid's division lemma. Now the question arises, how to use this to find the HCF of two numbers? That we'll see in the Euclid's division algorithm. Euclid's division algorithm. Let us see what it says. Euclid's division algorithm is nothing but it is used to find the HCF of two given numbers. The process is, first step, apply Euclid's division lemma to the given numbers. Say the numbers are c and d. Say the two numbers are C and D. So apply Euclid's division lemma to C and D. And the condition, like let us say that C is greater than D. Fine. So apply Euclid's division lemma to C and D. So I'll get something like this, that is C equals to dq plus of r, right? I can represent, since C and D are both positive integers and so they will satisfy Euclid's division lemma. So C and D can be represented as dq plus r, right? Second thing, if r is equal to 0 in this condition, if I got r is equal to 0, this implies D will be the HCF of C and D. If r is equal to 0, then D will be the HCF of C and D. Third thing, if r is not equal to 0, right? If suppose r is not equal to 0, then what you have to do? Apply Euclid's division lemma to D and R. Apply Euclid's division lemma to D and R and proceed further. Now again you have two positive integers D and R, so you can write some D is equal to some A times R plus of B. Fine. And if B is now equal to 0, then you can say R is your HCF. If B is not equal to 0, again you have to proceed further and apply Euclid's division lemma to the next set of steps. Let us take some example to understand how this works. Say I have two numbers 148 and 32. Say the two numbers are 148 and 32. Now I can write 148 as equal to 32 into 4 plus of 20, right? 148 can be written as 32 into 4 plus of 20. Now you can see here that the R20 is not equal to 0. Fine. So we have to continue our Euclid's division lemma process to the numbers 32 and 20. Now 32 can be written as 20 into 1 plus of 12. Again R is not equal to 0. So we'll again apply Euclid's division lemma to 20 and 12. So now 20 is equal to 12 into 1 plus of 8. Again this is not equal to 0. So we'll apply Euclid's division lemma to 12 and 8. So 12 is equal to 8 into 1 plus of 4. Again this R is not equal to 0. So we will apply Euclid's division lemma to 8 and 4. Now 8 is equal to 4 into 2 plus of 0. So finally our this R is equal to 0 and hence the HCF becomes this divisor 4. So I can say that the HCF of 148 and 32 is nothing but equal to 4. This is how this process works. Let us take another example to make it more clear. Say I have two numbers, say 124 and 24. Two positive integers. So 124 can be written as 24 into 5, which will give me 120, and the remainder 4. Again this is not equal to 0. So we'll apply Euclid's division lemma to 24 and 4. Now 24 is equal to 4 into 6 plus of 0. So we got the remainder as 0 in the second step only. Hence the HCF of 124 and 24 is nothing but equal to 4 itself. You can check whether this is correct or not by simple prime factorization method. 124 is nothing but 31 into 2 square and 24 is nothing but 2 cube into 3. So how do we find the HCF using this? HCF is equal to 2 square, the least power of the common factors available, which is equal to 4. Hence the method works.